All right, today we're going to dive into a really fascinating, kind of hidden problem that's happening inside your computer literally all the time. In a world of super limited memory, how does it decide what to keep handy and what's okay to forget? Well, the answer is a lot stranger than you'd probably guess. I mean, seriously, think about it for a second. You've probably got your browser going, maybe some music, a game, who knows how many tabs. And yet, somehow, your machine just handles it. It doesn't just fall over. The magic behind all that juggling is a set of rules or algorithms that figure out what data to keep and what to toss. Here's the best way to picture it. Your computer's main memory, the super fast RAM, it's like a small workbench right in front of you. And your huge hard drive, that's the giant warehouse out back. Now, you can only work with the tools that are on your bench. And every time you need a new tool from the warehouse, it takes time. It slows you down. The entire game here is to keep the right tools on the bench at the right time. Okay, so what happens when your computer needs a tool, a piece of data that isn't on the workbench? Well, it has to stop what it's doing and go all the way to the warehouse to get it. That little interruption is called a page fault. And our goal, the goal of any good operating system, is to keep those page faults to an absolute minimum, because every single trip to the warehouse slows everything down. So the big question is, when our workbench is totally full and we need to bring in a new tool, which one do we send back to the warehouse? Well, the most obvious solution is the one we use for just about any line you've ever stood in. First in, first out, or as it's known, FIFO. The logic here is, about as simple as it gets. It's like a line at the grocery store. The first page of data that gets loaded into memory is the very first one to get kicked out when we need more space. It's fair, it's simple, and it feels like it should work just fine. Let's watch how this actually works. As you can see in this table, the system gets a whole list of requests for different pages of data. With only 3 slots on our workbench, you can see it fills up pretty fast. Now, every single time a new page is needed, FIFO just blindly kicks out whichever one's been sitting there the longest. The important thing here isn't every single step, but the final score. For this job, we end up with 12 of those slow page faults. That's our baseline. Okay, seems pretty straightforward, right? But this is where the story gets really, really weird. What do you think happens if we try to make things better by just getting a bigger workbench? I mean, logically, a bigger workbench should mean fewer trips to the warehouse. That's just common sense. More space means you can keep more tools on hand, which should mean fewer page faults. But does it? All right, let's put it to the test. We're going to take a new sequence of page requests and run it on a system with a 3-frame workbench. We'll apply that same simple FIFO logic we just talked about. And when it's all said and done, we count them up. So for this specific job, a 3-frame workbench gets us 9 page faults. Not amazing, but okay. That's our number to beat. And now, for the crazy part, we're going to upgrade to a bigger 4-frame workbench. We give the exact same list of requests, more memory to work with. And we follow the exact same simple FIFO rules. And the number of faults, it goes up. We now have 10 page faults. More memory led to worse performance. And this chart just slams the point home. We gave the system more resources, more memory, and its performance literally got worse. The bar for 4 frames is higher than the bar for 3. This is the complete opposite of what you'd expect to happen. This totally bizarre thing actually has a name. It's called Belay's Anomaly. It's a proven, weird glitch in the simple logic of FIFO, where adding more memory can totally backfire. So the main takeaway here is, our simplest, most obvious solution, it's fundamentally broken. We need something smarter. So if FIFO is out, then what's the answer? Well, let's just imagine for a second that our computer had a superpower. What would the perfect, absolutely ideal algorithm even look like? The perfect algorithm would basically be a fortune teller. It would look at all the tools on the workbench, and it would just know with 100% certainty which one it can put away because it won't be needed for the longest amount of time. This theoretical powerhouse is called the optimal page replacement algorithm. So the optimal algorithm looks forward in time. The problem is, you can't actually predict the future, so it's impossible to build in a real system. It's really just a benchmark for what's theoretically possible. But it gives us a brilliant idea. If we can't look at the future, why don't we just look at the past? And that leads us to something called the least recently used algorithm, or LRU. So this brings us to LRU, which is kind of the practical, intelligent cousin of that impossible optimal algorithm. It works on a really simple but powerful idea. If you haven't used a tool in a long, long time, you probably won't need it again anytime soon. Let's see how it works. When a page fault happens and we need to kick something out, LRU doesn't care when the page first arrived. No, instead, it looks backward in time through the list of requests, and it asks, of all the pages I have in memory right now, which one has been sitting there unused for the longest time? And then it replaces that one. It's a strategy based on history, not just on who was first in line. So, LRU's whole game is simple. Get rid of the page that's been gathering the most dust. It's basically making a smart bet that the past is a pretty good predictor of the future. And you know what? For most of the things you do on your computer, that is a bet that pays off big time. So after looking at the simple but broken one, the impossible but perfect one, and the practical but complex one, what's the big lesson here? Well, it all boils down to a classic engineering trade-off. Here's the final scorecard. You got FIFO, which is super simple and cheap to build, but it's haunted by that bizarre Belay's anomaly. Then you have the optimal algorithm, our perfect but totally impossible benchmark. And finally, there's LRU, which give us great reliable performance, but it costs more. It's more complex for the system to keep track of everything. So at the end of the day, it's this constant balancing act between speed, intelligence, and cost. And this is exactly why it matters to you. Every single time you switch apps, open a new browser tab, or load a level in a game, your computer's operating system is making one of these decisions in a split second. The smooth, seamless experience you just take for granted is built on this very foundation, this trade-off between simple, fast logic and more complex, intelligent logic. So that leaves us with a final thought, right? The perfect solution is often impossible to reach, and the simplest one can be seriously flawed. And that isn't just a thing about computer memory. It's a fundamental question we have to face everywhere. How do we find that sweet spot between what's easy and what's smart? That's the real challenge. Thanks for watching.